Alright guys, so 2 days ago in the lab and yesterday in our class discussion and our little arts and crafts project with the compasses, we talked about the interference from two different speakers that are in phase. And when speakers are in phase, remember that means that they're both making compressions and both making rarefactions at exactly the same time. And that's what you always have whenever you have two speakers driven by the same source. So if you remember from our lab and our discussion, we talked about right here along the center line, this is what we would call M equals 0. And that would be a place of constructive interference. And the reason for that is that the path length of the two sound waves that came to you from each speaker would be, the difference between those would be 0. They'd be exactly the same path length. And then remember, if you travel up the line or down the line, you can find other spots that are loud and quiet. So up here we may have a spot M equals 1, which would also be a loud spot. And remember, that's a spot where the path lengths of the two waves coming from the two speakers differs by exactly one wavelength, and so we'll get constructive interference there as well. And a little further up we may have a spot where M equals 2, which would be another loud spot. So remember, anytime they're off by multiple numbers of wavelengths, that's going to be a loud spot with constructive interference. Now likewise, you may have a spot somewhere in between where M equals 1/2 or M equals 3/2. So what that would tell us is that the two path lengths of the waves are off by either half a wavelength or 1.5 wavelengths. And so what happens there is we get destructive interference. So that will be quiet. Now, if we know the frequency produced by the two speakers, and we know the distance L and D, it's actually possible to calculate the spot where you'll have loud or quiet, constructive or destructive interference. But the math can get a little tricky. So let me talk to you about how that's going to set up. So if we're looking for that spot where M equals 1, that first spot where we have constructive interference again, remember, we're looking for the spot where L2 minus L1 is equal to lambda. And so we can do that. We can set up an equation using Pythagorean theorem. So I'm going to write that out for us. Alright, so L1 using Pythagorean theorem should be the square root of L squared plus x1 minus d over 2 squared. And L2 should be the square root of L squared plus x1 plus d over 2 squared. And remember guys, x1 is the distance from that central line up to that first loud spot. And remember that d is the distance between your two speakers. Alright, so remember we need L2 minus L1 to equal lambda. Alright guys, so what we get is this fun equation here, where square root of L squared plus x1 plus d over 2 squared minus square root of L squared plus x1 minus d over 2 squared equals lambda, which is also v over f, where v is the speed of sound, approximately 340 meters per second, and f is the frequency of the tone that the two speakers play. And so what you'll find is if you plug in L and you plug in D and you plug in V and you plug in F, the only unknown is X1, and in theory you can solve for it. It's not very fun. So for that reason, people have come up with a more simplified way to do it. So let me erase some of these equations and show you guys the trick that you can use in certain situations to make your life much, much easier. Alright guys, so here's a trick that you can use to solve for this problem. And remember, the idea still is that L2 minus L1 has to equal M times lambda. And in our case, M equals 1, so L2 minus L1 just equals lambda. Alright, so what we're going to do is draw an extra line in here. And so what I've done is I've drawn a line from the midpoint of the two speakers up to that point where M equals 1, that first spot of constructive interference. And then I'm going to label this angle right here between that central line and the line going up to M equals 1, theta. And so then remember, what we want to do is we're looking for the difference between L1 and L2. Now this trick only works if D is much, much smaller than L. But if D is much, much smaller than L, then essentially that black line that I just drew between L1 and L2, L1 and L2 are very, very close to parallel. As long as D is much, much less than L, then we can make what's called an angle approximation by saying they're all pretty much parallel. And so what I'm going to do is I'm going to add a little triangle right down here. And then what you can realize is that the width of this triangle right here is that delta L value. Okay? That is how much longer L2 is than L1. And then like we were saying earlier, as long as D is much, much smaller than L, then this becomes a right triangle, and this angle up here is also very, very similar to this angle here, theta. They're approximately the same. They'll be very, very close, even though they're not quite the same. And so then what happens is that D times sine theta is going to equal that delta L value, which, as we said earlier, needs to equal m times lambda. And so now we just know that D sine theta equals m times lambda, once again, as long as D is a much, much smaller value than L. And then the last thing we need to know to be able to solve problems using this situation is that this angle theta right here is also can be solved for by using tan theta, which will always equal your opposite, which is x1, divided by adjacent, which is going to be your capital L. So we end up with these two equations that make our life much, much easier and keep us from solving that very complicated equation we had earlier. D sine theta equals m lambda, and tan theta equals x1 over L. So let's use that to solve a problem. Alright guys, so let's say for this problem we have two speakers that are 2 meters apart, and then 30 meters away we have this parallel line. And so right here is our spot where m equals 0. That's our central point where we're going to have constructive interference. And we want to know the value of x1, the distance you'd have to walk up that line to get where m equals 1, which will be our next loud spot with constructive interference. We see that our speakers are in phase and they're playing a tone with a frequency of 600 hertz. So the first thing we're going to do is solve for the wavelength of the sound wave. Alright, so it turns out that using a speed of sound of 340 meters per second and a frequency of 600 hertz, we get a wavelength of our sound wave of 0.56 repeating meters. So the next thing I'm going to do is I'm going to go ahead and draw that line going from the center of the two speakers up to m equals 1, and I'm going to label my angle theta. And so remember then, for this problem, D sine theta should equal m times lambda. So our first step is to use the information given to solve for theta, and we'll see that theta is going to equal the inverse sine of m lambda over d. So then we can plug in our numbers and solve for theta. And so what we'll see then is we get that theta is 16.46 degrees. And then after that, we know that the tangent of theta should equal x1 divided by L. So now we can use that to solve for x1. So when we do that, what we'll find is that x1 comes out to equal 8.86 meters. So from this central location here, we would have to walk 8.86 meters up our line until we got to the next loud spot of constructive interference. So remember guys, this is kind of a cheat equation as long as D is much, much smaller than L. So, so if we're going to use this equation, we need to make sure it works. So let's plug back into the Pythagorean theorem and see how well this comes out. Let's see if delta L is really equal to one wavelength. Alright, so as we can see, I've calculated L1, shown up there in red, and L1 would be the square root of 30 squared plus 8.86 minus 1 squared, which comes out to 31.01. And the reason that's 8.86 minus 1 is, remember, the distance from here to here is 8.86 meters, but from here to here is 1 meter. So the y component of L1 would be 8.86 minus 1. We can obviously see that my drawing is not anywhere near the true scale. Alright, now we're going to do the same thing for L2. Alright, so when I use the Pythagorean theorem to solve for L2, that one comes out just a little longer, as it should, to 31.58 meters. So we will see then that delta L, which would be L2 minus L1, is going to be 31.58 minus 31.01, which would be 0.57 meters. So we have a path length difference of 0.57 meters, and we can see up here that we have a wavelength of about 0.57 meters. So our approximation using this equation of d sine theta equals m lambda has worked in this situation. And most of the problems you see, it will work, and you won't have to go through and do all the work with the Pythagorean theorem to figure out the location. Alright, so I've left a practice free response problem for you guys to try today as your next part of your assignment. So good luck with that, and we'll talk about it on Monday. Bye.